Welcome to the third lecture. In this lecture, we talk about linear dependence and independence of vectors in Fn. If you take a vector a1 up to an in Fn, then you can write this vector as a1 e1 plus etc. an en, where ei is the vector in Fn with 1 at the ith position and 0 everywhere else. This concept of writing a vector v as a linear combination, as a sum of scalar multiple of a set of vectors, is called linear combination. So we define this here. v1 up to vm and v are vectors in Fn. We say that v is a linear combination of the vectors v1 up to vm if there exists scalars alpha 1, alpha 2 up to alpha m, such that v is equal to alpha 1 v1 plus etc. alpha m vm. For example, you can see that 3 1 is a linear combination of 1 1 and 1 minus 1, because 3 1 is equal to 2 times 1 1 plus 1 times 1 minus 1. And similarly, you can see that 4 minus 2 is also a linear combination of 1 1 and 1 minus 1. In fact, if you take any vector a comma b in F2, you can write it as a linear combination of 1 1 and 1 minus 1, as you see on the screen. But then this is not true for arbitrary two vectors. For example, if you take these vectors 1 1 and 2 2, you cannot write all vectors in F2 as a linear combination of these two vectors. For example, 1 0. If you take any linear combination of 1 1 and 2 2, both their coordinates will be equal. So here, if I take any vector which has coordinators a comma b with a not equal to b, that cannot be a linear combination of 1 1 and 2 2. We say that a set of vectors v1 up to vm, or array of vectors v1 up to vm, are linearly dependent if at least one of them is a linear combination of others. And we say that a collection of vectors is linearly independent if it is not linearly dependent, or in other words, none of these vectors can be expressed as linear combination of the others. Here you have to be careful that when we say it is not linearly dependent, it means that none of these vectors can be expressed as a linear combination of the rest. So from these examples that we saw, we can say that 1 1, 1 minus 1 and 4 1 are linearly dependent, and 1 1 and 1 minus 1 are linearly independent, because any linear combination of 1 1 is a scalar multiple of 1 1. For that, both the coordinates will have same real or complex number, so therefore it cannot be equal to 1 minus 1. A quick observation about linear dependence. Suppose you take m vectors in Fn and one of them is the 0 vector, then v1 up to vm is linearly dependent. This is because you can write vi, the 0 vector, as a linear combination of the rest of them with all the scalars being 0. So any collection of vectors including 0 vector is linearly dependent. Now if you take two vectors v1 v2, they are linearly dependent if one of them is a scalar multiple of the other. Think of this in R2 or R3. Two vectors are linearly dependent if one is a scalar multiple of the other. Or in other words, both of these are collinear. Similarly, if you take three vectors in R3, when are they linearly dependent? If one of them is a linear combination of the other two. So if you take two vectors and take its linear combination, what you get is the plane containing these two vectors. You can take this as an exercise. Think about it. Okay, try to prove it. So the exercise is that three vectors in R3 are linearly dependent if one of them is contained in the plane containing the other two, or the plane generated by the other two. Now let's prove a characterization that is helpful whenever we want to prove that a given collection of vectors are linearly independent or dependent. So the claim here is that a collection of vectors v1 up to vm in Fn are linearly independent if and only if for alpha 1 up to alpha m in F, alpha 1 v1 plus etc. alpha m vm equal to 0 implies that all the scalars alpha 1 up to alpha m are 0. What does the statement say? v1 up to vm are linearly independent if and only if the only way to get the 0 vector as a linear combination of all these vectors is the trivial linear combination, that is by taking all the scalars 0. Let us try to prove this. Suppose v1 up to vm are linearly dependent. What does that mean? It means one of them is a linear combination of the remaining. That is, I can write vi equal to alpha 1 v1 plus etc. alpha I minus 1 vi minus 1 plus alpha I plus 1 vi plus 1 plus etc. alpha m vm. Now taking vi to the other side, what you can write, what you get is alpha 1 v1 plus etc. alpha I minus 1 vi minus 1 plus minus Vi. Minus Vi is nothing but minus 1 times Vi. So when you write the vector minus Vi as a scalar multiple of Vi, it is minus 1 times Vi plus alpha I plus 1 Vi plus 1 plus etc. alpha m Vm. Now this is a linear combination with at least one of the coefficients not equal to 0, and that is exactly what we wanted to prove. So if they are linearly dependent, if they V1 up to Vm are linearly dependent, then there exists alpha 1 up to alpha m with at least one of them non-zero and alpha 1 V1 plus etc. alpha m Vm equal to 0. That's what we proved now. Now let's prove the converse. Suppose there exists scalars alpha 1 up to alpha m, not all of them 0, that is at least one of them is non-zero, and alpha 1 V1 plus etc. alpha m Vm is 0. Suppose alpha j is non-zero, then I can write Vj equal to minus alpha 1 by alpha j times V1 plus etc. Minus alpha m divided by alpha j times Vm. So we have now expressed one of these vectors as a linear combination of the rest, which means that V1 up to Vn, V1 up to Vm are linearly dependent. So this completes the proof of the theorem. Now a word of caution. If you are asked to prove that a set of vectors, a collection of vectors are linearly dependent or independent, or suppose you are asked to prove that it is linearly independent, you have to start with the assumption that a1 v1 plus etc. an vn equal to 0, and from there, using whatever data that we have, we need to conclude that a1 is 0, a2 is 0, etc. an is 0. Let us see an example. Are these vectors 1, 1, 1, 2, 1, 1, 3, 1, 0 linearly independent? So first, take a times 1, 1, 1, 1, 1 plus b times 2, 1, 1 plus c times 3, 1, 1, 1, 0 equal to 0. And we need to show that the only way this can happen is by getting a equal to 0, b equal to 0 and c equal to 0. So now the left hand side of this equality, we can write it as a plus 2b plus 3c comma a plus b plus c comma a plus b. Now this is equal to 0 comma 0 comma 0. Two vectors are equal if the corresponding entries are equal. So equate them, compare the last two equations, what you get is c equal to 0. Substitute in the first equation to get a plus 2b equal to 0. A plus 2b equal to 0 and a plus b equal to 0 implies b is 0, and therefore a is 0. So this proves that these three vectors are linearly independent. Now this linear independence is helpful when we do the system of when we consider a system of linear equations. One instance where it is helpful. Suppose I have a system of linear equations as shown on the screen. If you take the coefficients as vectors, then you get v1 equal to 1 2 minus 3 2, v2 equal to 2 minus 1 2 3, and v3 equal to 4 3 minus 4 7. One can see that the third vector is a linear combination of the other two. So the third equation in fact is redundant. We don't really need the third equation to find a solution for the first and second. So therefore, when you have a linearly dependent equation or a linearly dependent vector, we can discard that vector or discard that equation to find the solution of the system. Here we present a situation when a set of vectors are naturally linearly independent. A collection of vectors v1 up to vm in Fn are said to be orthogonal if inner product vi vj is 0 for all pairs of indices ij with I not equal to j. Now the claim here is that any orthogonal list of vectors in Fn is linearly independent. Suppose I take a set of all a collection of vectors v1 up to vm, non-zero vectors, and suppose v1 a1 v1 plus etc am vm is 0 for some scalars a1 up to am. We want to show that this implies that a1 equal to 0, a2 equal to 0, etc, am equal to 0. Now taking inner product with vi, taking the inner product a1 v1 plus etc am vm with v1, what do we get? We get a1 v1 inner product v1 is 0. That's because vi v1 is 0. Inner product vi v1 is 0 for every I not equal to 1. So the only remaining non-zero component in that inner product will be a1 v1. So a1 v1 inner product with v1 is 0, which is a1 v1 inner product v1 is same as a1 times inner product v1 v1. But inner product v1 with itself is non-zero because v1 is non-zero. Therefore a1 is 0. Now in the same manner you take inner product with each of these vi's. That will give us the conclusion that ai is 0 for each I. So this proves that a1 v1 plus etc am vm is 0 implies a1 equal to a2 equal to etc am equal to 0. That proves that v1 up to vm are linearly independent. So this concludes this lecture on linear dependence and independence.